This is the third part of the topic on the antiderivative, not antiderivative. This is the third part on the inverse of logarithm of the trigonometric function. So far, up to this stage, we have already explained the derivations of the formula for the derivative of arcsine and arctangent and also arcsecant. The derivative for arccosecant, arccotangent, and arccosecant can be easily obtained because we know that the arccos and arcsine form a pair within an identity. The arccos and arcsine, when they add up together, it's equals to 90 degrees. So is the arctangent and arctangent. When they add together, they forms 90 degrees as well. So is the arcsecant and arccosecant. So the derivative, obviously, of each of these pair is related. So, for example, here, if you take the derivative of the arccosecant, it would give you a negative sign when you take the derivative of arcsecant. So, knowing the derivative of arcsecant automatically give you the derivative of arccosecant, and so is for the other two relationships. So in practice, you don't memorize all these formula. You always remember that arcsine and arccos, they form a pair, right? So maybe I should write it in another sheet. So arcsine and arccos, they always form a pair, and then their sum is just 90 degrees. So from these very simple relationships, then the derivative of arccos is just equal to the negative of the derivative of arcsine. Likewise, cotangent and arcotangent and arctangent, this is arctangent, they also form a pair. So here the derivative of arctangent is just equal to the negative of the derivative of tangent, of the arc of tangent. Okay, so likewise the arcsecant x and arccosecant x, they also form a pair. So the derivative of arccosecant is just equal to the negative of arcsecant. Therefore, when you can remember this, you will automatically remember this because these two only differ in a negative sign. So if you can remember the derivative of arctangent, then the derivative of arctangent is just equals to that of arctangent with a minus sign, and the derivative of arccosecant is just the same as the derivative for arcsecant with a negative sign. So this is just a complete set of derivative for 6 pieces of inverse function for trigonometric. So now let us look at another example, which is to find the derivative of the tangent for the graph. So this is a graph of cotangent. So the graph of cotangent, if you can sort of like remember how this graph looks like, it's helpful. So let me try to figure out what is the graph of the cotangent. The graph of the cotangent would look something like this. This is not, this is the arctangent. So the question asks you for this arctangent, if x is equal to -1, right? So if x is equal to -1, at this point, what is the slope, right? And then if you have found the slope, then the values for the formula for the tangent line is just mx plus c, right? So m in this case is just the derivative of the arctangent at x equals to 1. So basically we need to find the slope at the arctangent of these functions at the values of x equals to minus 1. Once you have calculated the values of the slope, then you would like to calculate the values of the constant, where the values of the constant can be obtained by slotting in the values of the coordinate at this point. And the coordinate at this point is just x equals to minus 1, and also at the values of cotangent at minus 1. Right? So this is x coordinate and y coordinate. So you slot in x equals to minus 1, you slot in y equals to cotangent at minus 1, then you'll be able to calculate what c is. Now, once the values of the slope m and the intercept of c are calculated, that finish up the questions of the tangent line at this point of x equals to minus 1. So that is what for the answer. And before we end the proceed with the calculations, one thing that you should bear in mind is before you get any answer, you must aware to be a positive number, right? It's very obvious from the graph the slope is positive, right? It's just like this. So it's positive, it's not like that. So I think it must be, yeah, it's why no, this is negative. Okay. So we the derivative at x equals to minus 1 is, it must be a value which is negative. So if I proceed with the calculation and find the answer for the derivative at this point to be positive, then I'll be sure that that is a wrong answer. So so knowing the sign of the derivative at x equals to minus 1 by referring to the graph is a very good check for you to assure that your answer is at least not wrong. So let's see how you do these calculations from here back to these questions. So I need a graph to answer. So this is the questions that I want to do. My question is that I want to know what is the functions. So the function is y equals to arctangent, right? So this is a function of tangent, and I want to know the slope at x equals to minus 1. So first of all, I would then work out what is the dy dx for arctangent. So it so happened to be negative of derivative of arctangent. So for derivative of arctangent, this is what it is. Arctangent of minus x is equals to 1 over x squared. Okay, so this is an formula which is easy to remember. I remember this. Therefore, derivative of arctangent is just equals to minus 1 over 1 plus x squared. Okay, so in order to assure that my answer is correct, my just to make sure that I do not lead to a right straight. So here, yeah, so this is correct. So it is minus of 1 over 1 plus x squared. So equals to minus 1, x equals to minus 1, then the values for the dy dx would then be a values of minus 1 over 2. Right? So when x equals to minus 1, then can just see that the slope is just a values of minus half. So that is the first part of the answer. Then the second part of the answer is to work out the values of the tangent line, which is mx plus c, and the graph goes through a point of -1 and arc chord at -1. Right. So what is the values of arc chord at -1? Right. So this is something that I want to work out. So let me just call this A. I just call this B to be arc chord of -1. Right. So you can work out what B is by pressing your calculator. You give you some number, or you press Mathematica. But I would like to show you and demonstrate to you how you actually do that. Right? So, but before I work out what the values, exact values of B is, just to express Y as C in terms of Y, which is Y minus mx. So here, your Y is the values of B. Right? B is just the arc chord of -1 minus half, so which is plus half, and then you have -1. So this is B minus half. So that is the values of the intersect for the straight line describing the tangent line, and M is the slope of the tangent line. And I'm quite sure that this is not wrong, because my slope is indeed a values of negative, which I have anticipated early on. I've shown you early on, I expect the slope to be a negative number. So now this is almost done. So the answer for this, for C, is just equals to arc chord -1, then minus half. But what is values of arc chord of -1? Arc chord of -1 is workable, right? You can deduct the arc chord of 1 from a construction. So from here, you can just work out cotangent B is just equals to -1. So if cotangent B is -1, can you tell me what is the values of B? So this is again a very simple answer. You can just check out the table or from internet or from wherever. But let us try to reconstruct this answer from scratch by working out the solution with a help of the definition. Right. So cotangent of B is equals to -1. That's how do you translate these equations into a triangle? So I would like to calculate the values of B by translating this into the shape of a table. So let me see how I do it. Okay, cotangent of -1. So -1 means it is -1 -1. So this will be a ratio of like this. So let me construct a xy plot. This is x, this is y, and this is a point on the second sector in the xy. So here the values of x is negative, right? So if you have a coordinate of x and y, then the coordinate here y is positive and coordinate of x is definitely negative, right? So in that case, let me define my b. What is my b? So let me define my b to be like this, right? So if you still remember the definitions of the generalized trigonometric functions, if you define cotangent b to be like this, then cotangent b by definition is a ratio of the adjacent to the opposite, right? So the adjacent here is this value, which is the x coordinate value, and y, where x and y here refers to the coordinate of this point and coordinate of the y of this point, right? So this point, the adjacent for B, the angle B is this part is the adjacent, and then the opposite for B is just this vertical line, right? So I think this is the definition of cotangent. Yeah, so if it's tangent B, then it will be y over x. For cotangent B, it will be x over y. And here it is said to be -1. Okay, it is said to be -1. So this is the relationships. So here you can see quite clearly, if this is -1, then it just simply means that this is a length of +1, but since it's located on the negative side, so x is -1. So let me rewrite this triangle a little bit more clearly. It is just like this, and you have a point here, and then this is the values of the angle B, and here is -1, and here is also 1. So with this, then the cotangent B is just equals to -1/1, where this -1 refer to the length of the adjacent, which has a negative value in the x-axis, and the y here, 1 here is the length of the y, which represent the y coordinate of this point. Right? So now you have a very simple situations of a triangle where the side is 1, this is 1, and this is 90 degrees. Now what can you conclude for the angle of this triangle? It is then very easily understood that you have a triangle that is like this, that is like this, where this is a length of 1, this is a length of 1, right? So the -1 just refer to the absolute value of x coordinate, but the length on this side is just 1, and this is 1. So what you can say for sure is that this is an triangle which is of, I don't know what you call that, equal lateral. I'm not sure what you call that, but anyway, this is just a simple geometry which I learned in Form 2 that says that if this is 90 degrees, then for sure this will be like 45 degrees. Right? So this will be a 45 degree for from the geometrical symmetry. Then you work out this to be your 45 degrees. So this is your values of the angle B. Right? So if you have this angle of B, then you can work out quite easily the rest. Right? So then from here, what you want is this. What you want is to calculate the values of arctangent. Arctangent of -1. So this is not arctangent. This is what I want to find. Right? Arctangent of -1 equals to what? So the values is just equals to B. Right? What is B? B is just 45 degree, but not 45 degree. Okay, so this is 45 degree, this is 45 degree, and then B is just 135 degree. Right? So B is defined from here up to here. Right? So this is 45 degree. So from these very simple relationships, I can work out quite easily that the angle of B is just equals to 135 degree, which I think equals to 3/4 pi. So I might make mistakes on this, but I think it should be more correct. So this is a value. Why is that 3/4 pi? 3/4 pi is because 135 degree is equals to 135 degree divided by 180 times pi. I think that is what it means. Right? So in terms of radian, 150 degree is equals to 3 pi/4 radian. Okay, I hope that I'm not making error on this. I think it should be correct. So that is the answer for the cotangent, which is just like this. So the values of B is just a number here. This is just equals to 3/pi/4 for this arctangent minus 1/2. Right. So the values of the tangent line should be just -half x plus 3 pi/4 minus 1/2. Okay, so that is my answer to the questions of this part. So this is the answer to the questions. That I think the answer is the formula will be just -half of x plus 3 pi/4 minus half. Okay, so this is constant. Now you can check this and see whether I have answered this correctly or otherwise. So that is the example 10. So the next thing is to proceed with the integration. So the integrations of the for the arc functions could be easily obtained from table 7.3. Right? So from 7.3, you have all the derivative relationships, and from this derivative relationship, then you can easily sort of like derive the the antiderivative version of this. So for example, just an example, let us take this example. You have d du of arc sine, so d dx, not d du, d dx of arc sine okay, so d du of d dx of sine u is equals to du dx times 1 over square root of, I think, 1 minus u squared. Okay, so just double check. So that is the original derivative for these versions. So you can easily obtain the sort of like antiderivative, right? So this is the derivative versions. The antiderivative version of it could be easily obtained by using the same trick that I mentioned earlier on. So just to simplify my working, I just call arc sine as 1 over u. So arc sine of u as y, so that I have dy dx equals to du dx, and then have a 1 over 1 minus u squared. So here maybe I rewrite this in a more neat manner, just to change the positions of the 1 over square root of u squared. Okay, then I have a du dx. So on the left hand side and right hand side of this equation, I multiply with the differential of dx. I think I have used this trick before. So here, this is the product of dy dx multiplied with differential dx. So this whole thing will give me dy, and then this is just equals to, now this is the product of du dx times dx. So it is then a differential of du. So you have a du with square root of 1 minus u squared, right? So that is how you get these results. Then, so dy is that. Then you take the antiderivative on both sides. So this is a symbol that says I am taking the antiderivative of dy, and the antiderivative version of this, after you have taken the antiderivative, then I get this relationship, which is quite straightforward. Let me write it on the upstairs. It is then equals to, now integration of this antiderivative of this will be just y. It will be just equals to dy du of square root of 1 over u squared. Okay, and what is dy? Y by definition is just my antiderivative of u. So that is the results. But since this indefinite integral forms is representing the collections of all antiderivative, therefore I have to add in a constants on the right hand side. So that is how you derive these relationships from the integration version, right? So you start off with these integrations, then you end up with this very simple rule that if you have integration of du over 1 over u squared du, then you would get arc sine of u, which is just what this formula is about. Right? So this is the formula of arc sine of this. Right? But the formula that you see here is slightly different than the formula I shown you here. So this is du of square of 1 over u, but here this is a square instead of 1 square, but the rest are the same. So if you compare these versions and my versions, you find that this is true if a is equals to 1. Right? So you set a equals to 1, then this formula that is shown here is then just exactly the same as what I have obtained here. But you can derive from these versions into this version with as a quite straightforwardly by using a simple substitution. So let me try to see how I can do that. Well, let's see if I can do that for you. So let us start from these simple rules, these simple relationships. Then I'll show you how you get to the equation number 1 from this. So this is a formula that I just derived from the derivative versions. Then you can generalize this by letting u equals to u over a, right? So just change a variable, introduce a variable. I don't know what you call. Let's say you call it a q. Okay, so you introduce q to be u divided by a constant. By a is just any constant. So if you do like that, then easily you would be able to show dq variable is just equals to du over a. Then you just rewrite these equations in terms of q instead of u. So here the left hand side is du. Du is just a times dq, and then downstairs would be then 1 minus u squared. So 1 minus u squared is let's see, 1 minus u squared is 1 minus u is aq, right? So it's aq square q, right? So that is u squared. So from here u is just aq, right? Easily u squared is just a squared and then q squared. So on the left hand side, I'm still working on the left hand side, is then equals to a times dq. So I'm going to pull out the q, but I think this is not a good replacement. So here I have made a good judgment when I introduce q to be u of a. So maybe I should change my strategy. I should introduce u to be aq. So q equals to au instead of q being u over a. So it's just a reverse of my choice. So I'm sorry about that, but I think it just demonstrates to you this is just a usual trial and error method. So you can't get things to be 100% correct in the first shot. So we have to revert this and then come back and work it again. So a process of trial and error, and this is also a process of solving the problem. So I don't getting the wrong answer in the beginning, as long as I finally get to the correct answer. Okay, so so let me introduce q. Instead of u over a, I'll call this ua, right? That will make dq equals to the constant a du, right? So this is just introductions of a new variable. Multiply the variable u by a constant a, so that on the left hand side, which is du, would then be equals to dq, and then you have a factor of a, then divided by 1 minus u squared. So so u is just then q over a. So u squared is just equals to q squared over a squared. So downstairs I have 1 minus u, which is q squared over a squared. So I think this is the more accurate, more correct way of doing things. So I'm still on the left hand side. So I have 1 over a, then the dq over. So I'm going to take out the q squared, a squared minus q squared. Then the a would be go out, then the a would get cancelled off. Okay, so that is, I think, a correct statement. Yeah, so that is what happened to the left hand side. So now I have to come back to the right hand side. So the right hand side is this. So let me work out some space for my right hand side. So right hand side formula is arcsine of u. So arcsine of u plus c is then u is just equals to q over a plus c. Okay, so now I have everything expressed in terms of q. So here is just equals to the right hand side, which is just arcsine of q over a plus a constant. So that is almost there. We are almost there already. So this is a relationship that relates the variable q. And if I don't like this, I can always put the q back. Then it will become just put u back. Yeah, I think you can just put u back into the q. So I just rename q. I change it with the same variable. So I just call this x. Right? So every q that I see on the symbol, left hand side and the right hand side, just replace it by x because this is just the same, right? So instead of calling q, I call it x. Then this is just a square. Sorry, I don't call it x. I think I should call this, because this I just call this u. Okay, so this will be just du. This will be a square minus u square. Then the right hand side will be just sine of u over a plus c. So this is the versions. Okay, I think it's not done yet. There's a mistakes in the share screen. So let me revert to my right. I have fixed my screen. So this is the versions in terms of q. So I just replace the symbol of q by u. Then I get this very simple formula, which is just a proof. Just the versions of the formula, equation number 1, which is generalized, which is a general versions from these versions, which has a constant of a equals to 1. If the constant is not 1 but a instead, then you just have these expressions. Right. So same thing for the case of arctangent. So maybe I'll just demonstrate one more time, but I will not do it for the arcsecant. I'll just do it for arctangent. So for arctangent, we have this formula of arctangent to be du dx over minus, to be 1 plus u. Now I would like to repeat the derivations for the integration functions. That's one. Which is the second equations from the differential version of it. So this is the differentiations of arctangent, and from here you could actually show it to arrive at equation number 2 shown on the screen, which is this one. In these versions of equation 2, you have an a, but in this equation here, the derivative has no a, but it's just only in terms of u. Just wait for the screen to show up. For some reason, the screen has been very slow to show up what I want to show. Okay, so I'm going to derive this step by steps to integrate these functions. So let me call out a WordPad to show me this relationship. D dx of arctangent u equals to du dx over 1 plus u squared. Okay, so let me write down the formula for this d dx dx of arctangent. Okay, this is arctangent of x is equals to du dx divided by 1 plus x squared. Okay, so again, I'm going to repeat the same tricks. I'm going to multiply, well, before I multiply, I'll just call this y to be just the arctangent of x. Then the left hand side will be just dy dx, and the right hand side will be just 1 over 1 plus x squared du dx. And on both sides, I'm going to multiply by dx. I'm going to multiply by dx. The product of dy dx times dx is again the differential of dy. Then the right hand side here is just equals to 1 over 1 plus x squared. And then you have a du, product of du dx. Dx is just then the du. So from here, I'm going to take the antiderivative of the versions. So the antiderivative of the y would just be equals to the antiderivative of the right hand side, right? So it will be just equals to, I think there's something not right here. I think this is not 1 over x, but this should be 1 over u. So I think that is my mistakes when I write down this equation. This will be u squared, and this will be just u squared instead of x squared. So it will be u squared. Okay, so I think that's the more correct way of the formula. This is u, not x. So this should be an u, not x. So that is, again, this should be u, not x. Okay, I think the rest of the derivative would be just correct. And this is 1 over u instead of 1 over x. Okay, so then the right hand side will be just equals to the integration of du plus 1 over u squared. So this is translated into saying that this is equals to y. Okay, so on the left hand side, here this is equals to y plus c equals to du 1 plus u squared, right? So this is the right hand side. It's not changed, but the left hand side is just the function of y add with a constant to represent the collections of the antiderivative represented by dy. This is actually the antiderivative of 1 with respect to the variable of y, right? So when you differentiate this, you get back 1. So that is, by definitions, the antiderivative of 1 with the variable y. So that would then give you a very simple relationships that says du over 1 plus u squared is equals to arctangent of u plus constant, right? So this is the relationships in terms of u. Then we can then generalize it by introducing u, introducing a variable of a into u by saying q equals to ua. Then I'm going to rewrite the equation upstairs in terms of q, right? So let's see how you do that. Maybe I am correct this time, maybe I am not. If I'm not, then I'm going to redefine like q to be u minus a instead of a u times a. But basically, if it's not u q equals to u times a, it will be q equals to u minus a, okay, u divided by a. But let us try this anyway. If you're faster than me, then you can see whether I should define this as u times a or u minus a. So here my dq is just equal to the constant a times du. So the left hand side is just du is just dq over 1 over a, and then you have 1 plus u squared. So this is 1 plus u is q over a squared. I think this is more or less correct, and this is arctangent of u. U is just q over a. I think more or less I am correct already. So I just have to simplify this slightly. This is just equals to dq, and then I'll just multiply the a to 1 here is a squared plus q squared, then the whole thing divided by a squared, right? So it is divided by a squared, then it's a squared upstairs, there's an a downstairs. So when you cancel off, then there will be an a upstairs. So this will be an a in the numerator. So it's a like that. So that is equals to arctangent of q over a plus a constant. So let me add the constants. Plus a constant c. So I'm going to then move the a from the left to the right. So this will be moved to 1 over a like this. After that, to make things look slightly more comparable to what you have seen in the previous slides, then I just relabel q with the label u, right? So that you'll be more happy to see that. So that is then is du over a squared plus u squared is equals to A times arctangent of U over A plus a constant. Right? So that is how you get the integrations of du divided by a square plus u square to be a arctangent u over a plus c. So I think that is the proof, which is this one. Okay, I think there is a factor of 1 over a downstairs, and there's a q u over a downstairs, and then you have a plus u square of. Okay, so I think that is equation number 1, and so I have already shown you how you can prove equation 1 and 2, and then you can try to see if you can reproduce equation 3 for yourself using the trick I just mentioned. For example, you can reproduce this equation 3 by referring to these equations. Right, so just move from here, you integrate on both sides, then you get a very simple results that is very similar in this form. So by just looking at this form, you will be more or less able to know what the answer is. That is, this would be looking like du over u of u squared minus 1. It will just give you secant square of u. I think that is what you can straightforwardly write down based on this relationship. So the integrations with respect to u for a function of 1 over u times square root of u squared minus 1 is just an secant of u plus a constant. And then you can generalize it further by, say, I think setting u to be just u multiplied with a constant a. Then you just rewrite everything. Then you'll be able to arrive at this result. Right? Okay, so I leave this as an exercise for yourself. So when you study mathematics, it's not good that you just memorize a formula. It would be strongly encouraged to derive all this formula and convince yourself that at least you have tried it at least once for your once a lifetime, right? Or else you would not have any chance to do this. Actually, it's not that difficult. Now, doing this exercise provides you with a chance to prove yourself that you can think, work out the mathematics all by yourself. So this is an example 11, example 13, and example 13 as well. Okay, so let us look at this example. It's nothing but just the straightforward applications of the formula. So we have a situation of integrating square root of 1 over square root of 1 minus x squared. So mind you, when you look at these integrations, the formula that we are looking at is a formula of the form that has this sort of form. So let me revise what you are looking for. You are looking at the integration of this form, I think u squared minus a squared. Then it will give you an arc sign. So this is basically this a squared minus u. So a comes first, then u come later. That will give you an arc sign. I think this will give you an arc sign functions. I think u plus a constant. I think maybe there is an a somewhere. Yeah, so there is an a in these definitions. Okay, so then you are looking also for integration of the form u square of, I think, a square plus u square. So that will give you an arctangent. I think here is u over a plus constant. I'm not sure. I have to check and see whether this formula is correct. Yeah, I think that is the second part. So when you see integration of this form, then you know that the result, the integration is in the form of arctangent. And then the other one is you have integration of this form du u square root of in this case is u square minus a square. So this is in contrast to the previous case for arc sign. For the arc sign, you have the downstairs as a square minus u square, but here you have a magnitude of u, and you also have u square minus a square. I think this will give you arc cosecant, arc cosecant, secant, arc secant. I think arc secant, if I'm not mistaken, arc secant of u over a plus a constant. So let's see if I am correct. Yeah, arc secant. So it just yeah, I think 1 over a 1 over a, so there is a factor of 1 over a that is missing, 1 over a, and then u over a in the arcsecant. So I think that is, yeah, I think that is correct. So usually the magnitude of u that is written here sometimes is not written explicitly. So if this is the case, then you'll be just an u. So it just be an u. Okay, so when you see this sort of forms, recognize that it is a result that you can straightforwardly write down the solution. So here we have this sort of situations. So here your a is just equals to 1. So in this case, we have an integration of the form du of a squared minus x squared. Right? So it's just that here your u, so I think this is du. Right? So here your u is just equals to x, and then here your a is just equals to 1. So this would be just equals to arcsine function. Arcsine function is a squared minus u squared. So this has to be remembered. So I remember this, don't know when I was Form 6, I still remember it. So for these equations, integrations of dx divided by 1 minus x squared is just equals to arcsine of x, right? And then if you were to put in the values, then you just put in the values of here, the limit here is square root of 2. So here the limit, I think I need some space to write 1 over, well, right, okay, here, yeah, so here it is limit of square root of 2 over 2, and upstairs is a square root of 3 over 2. So you have to evaluate this at square root of 3 over 2 and 1 over square root of 2. Okay, so what is this? So to get the result for this, then you have to either press your calculator or you look up the theoretical value for this. So let me see if I can remember this. I will try to produce answer for you on this on my WhatsApp. So this is the values I need to evaluate based on the previous slides. So you are supposed to find what is the values of arcsine of square root of 3 over 2 minus values of arcsine of 1 over square root of 2. Right? So if you can remember this quite well, then this is just a square root of 3 over 2. Arcsine of square root of 3 over 2, you can either ask the calculator or you remember from the table that we mentioned. I think we have mentioned this table earlier on ago. So this is sine of 60. Right? Sine of 60 has pi square root of 3 over 2, right? Remember this? Sine of 60. Sine of 60 is this, right? Sine of pi over 3 is sine of 60 is square root of 3 over 2. I think sine of 60, yes, it is this. So I remember this, or else you just have to know figure out yourself how to do this. So this is just pi over 3 minus this is sine of 1 over arcsine of 1 over square root of 2. So can you recall what is the values of what is the values of theta when you get 1 over square root of 2? Okay, I think here the x is just angle of 45 degree. Right? So this is 45 degree. 45 degree is pi over 4. So I hope that I do not remember this wrongly. So that would be just become pi over 4. Then it just become pi over 12. I think 4 minus 1, yeah, it's pi over 12. So the answer for this is just this one. So I'm working it out for you to demonstrate to you it is possible to get the answer for the arcsine evaluated at this value and this value without a calculator. If you can remember your specific angle for arcsine yourself. Right? So this part, if I'm wrong, then you can just always correct yourself, not correcting me. I'm just demonstrating it. So it doesn't matter if it's wrong. But the most important thing again is your concepts and your working, right? Not really my calculations. Right? I don't mind if my calculation is wrong, but I just want to demonstrate the process. So sometimes when I teach you, I tend to demonstrate the process of working, even though it's wrong, but just hope that the process can give you some hint or some idea or some feeling how the calculation is done. So again, when you look at this situation, you have integrations of the form of a squared plus x squared. This is the result for the arctangent. So I think this is x over a and 1 over a, if I'm not mistaken. Okay, so that is the result that could be obtained from here. So you have a squared plus u squared. So here the u is just my y. So here the u is just x. So you just set u equals to x. Then this equation number 2 will then reduce to these equations. So so you look at this one, the answer is just quite straightforward. The answer will be just equals to the integration, which is arc of x over a. So the a is just 1, obviously, and it's just arctangent, and then you have to evaluate the arctangent at 0 and 1. Then again, it is up to you of how to work out the derivative, the values of the limit at these 2 points. So do you know what is the values of arctangent of 1? Right, so I think so. So this is just equals to arctangent of 1 minus arctangent of 0. Right? So arctangent of 1 is just 45 degree. Right? The tangent of 45 degree is just equals to 1. Yeah, I think tangent 45 degree is equals to 1. So this is tangent of 45 degree, and then arctangent of 0 is just 0, right? So tangent of 0 is just 0. So then arctangent of 0 is just this one. So it's just equals to pi over 4. So again, I do not guarantee that my answer is correct, but you can always figure it out yourself if this is correct, if my working is correct. So again, here you recognize this to be just in the form of the integration that is cosecant. So this is the secant. Okay, let me write this more accurately. So this result is the integrations of the x over x, and then x squared minus 1, and then the x is so just make sure that the x is okay. I think this is okay. So that is just equals to secant. I think this is arcsecant of x. I think that is what it is. And then you just have to evaluate this between 2 of square root of 3 and square root of 2. So just to double check that if this is correct, so I think the formula that you have to use is this form, right? So just substitute, replace u by x and a by 1, then you get to this formula, right? So yeah, so that is quite true. So here you just set u equals to x, a equals to 1, then this formula number 3 would just become like this one, will just become like this. Then this is answer. So then you have to take the difference between the arctangent. So this is just arcsecant of square root of 2 minus arcsecant of 2 over square root of 3. So I think this one is, I'm not sure, I think it is 1 over square root of 2, it would be 45 degree. 1 over square root of 2, 1 over square root of 2, I think it will be pi over 4, I think 45 degree. So I do not guarantee that this is true, but I think sine 45 is just square root of 2. Sine 45 is square root of 2, then this is equals to sine of cosecant, no, I just don't know. Okay, so I just leave you with what exactly is this value, and then you just figure it out for yourself. Okay, it should not be very difficult unless you just press the calculator, you get you the answer. Okay, so maybe I should do a better job. So since I have a Mathematica, why don't I just use Mathematica to tell me what is the arcsecant of square root of 2. Okay, so I think square root of 2 is what I'm looking for, right? So I'm asking for what is square root of 2. So Mathematica can give you square root of 2. It looks like this. Okay, so this is just 2. So square root of 2 is like this. So I'm asking Mathematica, can you tell me what is the values of arcsecant, right? Arcsecant. Arcsecant of square root of 2, it should be just pi over 4. So I think I'm correct to say just now that arcsecant of square root of 2 is pi over 4. Then again, you can ask Mathematica to give you the values of arcsecant. In this case, the other limit that we are going to calculate is just 2 over square root of 3. 2 over square root of 3. So I think it will give you the exact value. The values of arcsecant of 2 over square root of 3 is just pi over 6. Okay, so that is the correct answer for the values of the limit. So let me go back to my iPad to get to my original calculations. So here is it. This is my original calculation. This is just pi over 4. This is arcsecant of square root of 2, and this is pi over 6. I think. Okay, so it ends up to be 6 minus 4 is 2, 1 over 12 pi. Okay, so that is the result of the integrations for this calculation. So I think the answer here is 1 over 12 of pi. So again, we can do a better job by checking the answer for these calculations using mathematics. Okay, here I am going to share my screens on my Mathematica. So I think you can see my share screen now. I'm showing you my Mathematica screens, which is to integrate these functions that I want to integrate. So the original function I want to integrate is this, right? It is 1 over x, or this is the one I'm talking about, and it's going to integrate from 2 over square root of 3 to square root of 2. So this is how you define these functions in Mathematica. I just showed you in a more accurate way. Okay, so that is how it is defined. Maybe I should make this slightly smaller. Okay. So this is the definitions of the functions to be integrated. It's not seen clearly. I have to do a better job by showing the screens. Okay, I think the screen is not shown properly. Okay, I think it's like this. Here you have, so these integrations that I want to integrate. So I integrate 1 over the square bracket, and within this bracket is x times square root of x squared minus 1, and integrate with respect to x from the lower limit of 2 over square root of 3 to square root of 2. So you can actually carry out this integration analytically and give you an exact values of pi over 12, which is just what I have shown you earlier on. The last slides that I want to discuss is the integrations of this sort. It looks a bit weird because it doesn't look like it is of the form that is agreeable with any of these three, right? So here the integration has a factor of square root of either a square minus u square or a square plus u square, or in the form of u times square root of u minus a square. Okay, so but if you look at the integration slightly more carefully, it is actually in the form of a square root of 4x minus x squared. Okay, so if you look at this 4x minus x squared, you can actually complete the square, right? So you can convert this into a form which is like a squared minus x squared, right? So you can actually convert this into the form that looks something like, I think, a squared minus y squared. Then you have a square root, 1 over. Then you'll be able to use the integrations formula for the arctangent. So for this particular example, what you need to do is just to convert the denominator of square root 4x minus x squared into into the form that looks like a squared minus x squared in the denominator. Right? This is what you want. Right? So once you have this factor in your integrations, in the integrand formula, in the integrand functions, then you would be able to use a arctangent, arcsine formula for this integration. So you have to perform some kind of conversion. So this is a trick, right? So you have some, given some integration, you have to look at it. How would you want to perform these integrations? So you have to try to see if it's possible to convert the integrations into the form that is allowed, that is conducive for you to use any of these integration. So for this particular example, you look at the integration form like this, then you know you have to actually refer to this formula. So you have to convert the equations into the form of a square minus u square. So this could be actually easily done if you know how to convert the square. Right? So you complete the square by using these tricks. So let me write it here. So here you have 4x minus x squared. So what you want to do is to think of a way of a constant square, right? So think of this as, I think, into a form of a squared minus y squared, right? So so you do it one by one. So if you do one by one, then you can just follow the tricks that I'm doing here. There are many ways, but there's no strict way of doing this. So you have 4x minus x squared. So you pull out the x, the x, that is minus 4x. Then you just let the minus sign to stay outside. Then this is a quadratic function, right? So you just complete the square for the quadratic function. So what you do is you just add 2x, then you square it, right? Then when you open up the square, you should have the values of 4x. So if you minus this with 2, then this will give you a factor of minus 4x when you open it up. But x minus 2 square, when you square, you have additional values of 4. Therefore, you have to minus away the 4. Right? So this is how you perform the so-called completing the square. You do the complete of square, I think, when you was form 4, form 2. I think maybe it's form 4, form 2. So it's a standard mathematical tricks that you could do. So then you just write this as 2 squared minus x minus 2 squared. Right? So now you are able to convert these integrations in the form into here. Right? So you just introduce a variable of u to represent x minus 2. So with this, then you'll be able to easily translate the integrations on terms of x into the integrations in terms of u, right? So just substitute u equals to x minus 2 into here. So this factor become x minus 2 squared become u squared, and this become 2 squared. So this is just an integration in the form of du over a squared minus u squared integrations. So you get sign of u over a, I think. So here the answer is just quite straightforward. But before I proceed on, I just want to double check my formula if it's correct. So I think the formula is arcsine of a over u. Yeah, I think this is the one that I'm looking for. Okay, so this will be a factor of u over a. So here the answer for this is then equals to arcsine of u over a. Here the u is just u, a is just equals to 2, right? So that is the answer. So I think that's the answer. So this is just equals to you just substitute it back, then you get the answer. U over 2 is just arcsine of x minus 2 over. Okay, I think you have a constant as well. That's a constant. So that finished up the chapter on these integrations. So this is another example. Not sure, I think this is not the end yet. There's another example. So here again, you just have to substitute u by ex. So when you substitute ex by u, then this integration just become this form. Then du will just become, sorry, the integration with respect to x can then be converted into integration with respect to u. So you just follow this these instructions, that will get you a very simple answer. So finally, you get to this form that is like this, right? So this is a form of du over u square root of u squared minus a squared. Right? So if you have this sort of integrations, then it's understood then your a is just equals to the square root of 6. Then the answer for this is then the arcsecant. I think this is, yeah, this is arcsecant of u over a, and then with a factor of 1 over a. So that is the formula for this particular case, right? So you have this 1 over a and arcsecant of u over a, that then give you the values of 1 over square of 6 arcsecant of u over a. So where is your u? Your u is just e power x, and then your a is just square root of 6. So you have also this with a constant. Okay, so that is the answer for this integration. So the tricks here is, again, recognize that these terms can be expressed into the forms of this, so that you can use the arcsecant integration formula. So far up to this stage, we have learned all the definitions for the inverse function for the trigonometric functions, and from there we learn how to calculate its derivative, and from its derivative it allows us then to have a formula, a set of formula that can perform very complicated integration, right? So if you have integration that is in this form, then the answer is in the form of arctangent, arccosecant, arcsecant, arctangent, and arcsecant, arctangent, and arcsine. Okay, so that's all for this chapter. Then I'll proceed to the next topic for your viewing.